So I first wish to thank Vlad for the kind invitation. It's a great pleasure to be here doing mathematics in Chebyshev laboratory. So I'm talking about extreme values in the branching random walk. And it's based on joint work with A.D. Aide-Kun and Yue-Yun Hu. Both are in Paris. So let me start with an example. And I'm afraid that probably I will stay just with this example. So the example is our model. So it's a simple example of branching random walk. And before I start, maybe I'll take just 1 meter of space to remind you something which probably you know for a long time. It's the example of a usual random walk. So this is what happens with the usual random walk. It means that you have independent and identically distributed random variables. So I guess if you know a few basic things about probability theory, this is more or less the simplest probability model you can think about when you have random variables which are jointly independent and which have exactly the same distribution. And what I'm interested in is the behavior of the sum in the first n random variables of this sequence of random variables. And the questions I'm asking myself is about the asymptotic behavior of this sum. And this sum usually is referred to as a random walk. So this is what people usually call a random walk. And so in my case, I'm still interested in the model of random walk, but what's more complicated is that I have a branching mechanism. Okay? So let's recall what happens with the usual random walk. So if I assume the existence, oops, maybe I should put it here. If I assume the finiteness of the second moment, I only care about the first one because everyone is assumed to have the same distribution. So I only need to check the second moment of the first random variable. So if I assume that everybody has a finite second moment, then I say that, okay, if I want to study the behavior of this random walk, all I need to do is to take a very simple linear transformation, which I call xi tilde, which is just xi, but I remove its expectation, which is the same as the expectation of xi1, and I divide it by square root of the variance of xi. Okay, you are going to tell me that I'm not allowed to divide by something which is zero. So if the variance is zero, then I'm in the trivial case that everybody is the same constant. Okay, it's not a very exciting situation. So implicitly, I'm assuming that not everyone is the same constant. Okay? If I make this very simple linear transformation, then I realize that I'm in a very simple situation where I still have a sequence of independent and identically distributed random variables. But now the expectation is 0 for tilde, and the variance is 1. Oops. So if I want to study the usual random walk, as long as I assume the existence of the second moment, then usually without loss of generality, I can assume that expectation is 0 and the variance is 1. Otherwise, all I need to do is to do a very simple linear transformation, which everybody knows what to do, and I immediately get to this very simple situation. Now I need for 1 to present you the model of branching random walk, and for 2 I need to introduce a similar assumption. Okay, so let me introduce the example of branching random walk. I put it. It's a random process. In my case, time is discrete, so this is time. By discrete, I mean it's indicated by natural numbers including zeros. At the beginning, there is one particle across, represents the position of a particle. At the beginning, there is one particle starting at the origin, so this is space. In my case, space is just one dimension though. And at time 1, if it's a usual random walk, then at time 1, just the value of psi 1. But in my case, I have a branching mechanism. Sorry, oops, it's hidden there. So I need to introduce a branching mechanism. And I will study just the simplest example of a branching process in the case that the branching mechanism is binary. So it means that every time a particle splits just into 2. Okay, so in my case, it will get 2 values. And I assume that this height and that height, these are 2 independent random variables, each having the same distribution as a generic random variable. Let's call it psi. Yes? Okay, so this is what happens at time 1. So I have 2 random variables which are independent and which have the same distribution as psi. And at time 2, both of them are going to split into 2 more pieces. And this guy is going to give 2 children. Oops, it's not necessarily the same. Let's say this one, that one, and this. Oops. And again, assume that the displacement of each new particles are IID random variables, and they all have the same distribution as psi, and so on and so on. So maybe that's it. So at time 3, I have exactly 8 crosses representing the positions of the 8 particles. So more generally, I'll use V of x to denote the positions of these particles. So the absolute value means the generation of the particle x. So V of x is the position of the particle x. X is a particle in the nth generation. So in this example, you see that the number of positions is 2 to the n. So I have 2 to the n, well, in my case, n is 3. So I have 8 positions, and that's it. And this collection of random variables is called a branching random walk. So that's the definition of my model. I hope it is clear what I'm interested in my talk. So you see that what I have written on the left-hand side is really an extension of the usual random walk, except that now the number of random walks, if I stop at the nth generation, is 2 to the n instead of just only one single random walk. Yes? Okay, so for the usual random walk, I had the usual assumption is that assuming the existence of second moments, then I said that after doing a simple linear transformation, I can always assume that expectation is 0 and the variance is 1. And here I have some similar assumption. So this is an assumption which I assume from the beginning until the end. So I'll give it a name. I call it assumption star. So, whoops. I will assume the existence of the second moment, except that for branching random walk, the existence of second moment, the form is slightly exotic. And since I will never need the exact form of this integrability, so I'm not going to write down exactly what the exact integrability condition is, because I will never need it here in the talk. Anyway, it's not very interesting in itself. I don't think it will perturb anybody. Under this moment condition, then I claim that you can always assume that expectation is 0 and variance is 1. But in the language of branching random walk, now the form is slightly different. I'll start with this one, saying that the variance is 1. I'm summing over the two particles in the first generation, and I take the sum over the exponential to the minus of their positions. And this is the analog for branching random walk of this second piece of conditions. Of course, you are going to tell me that, okay, I mean, you are a very peculiar person. Why do you want to write it here, write it like this? And for me, it's clear that I have two independent copies of random variables random variable xi. So this is exactly the same as saying that twice expectation of e to the minus xi. It's exactly the same, okay? So if you want, the first part of the assumption is saying that twice of this expectation is 1. So it means that this expectation, I'm assuming that it's 1/2. Okay, I prefer write it here because I think in 10 minutes, everybody will find it more convenient to write it this way. Anyway, for the moment, you will get the impression that I'm making your life complicated, but it's not true. The analog of saying that the expectation of 0 is saying that this expectation is 0. And again, if you don't like the writing, I mean, in this form, it's exactly the same to say that twice of expectation of xi, e to the minus xi is 0. It's the same thing. Okay, so the two together forms the basic assumption, which I call star. The integrability condition, which I haven't written down, somehow is there to ensure that both expectations have some sense. I mean, they are well defined. Actually, it's slightly more than that. We'll see later. Okay, so it's a very simple exercise, which I'm not going to do it. Assuming that, so if you have a real valued random variable xi, such that this expectation is 1 and this is 0, then by using Jensen's inequality, then it's a very simple exercise which you can give to all undergraduate students, saying that they will imply that the expectation of xi is strictly positive. Nothing guarantees that it's finite. It's possible that it's infinite. So this is a simple exercise of Jensen's inequality, saying that. So under my assumption, actually, the expectation of xi is strictly positive. Okay, so that's more or less what I want to talk about the assumptions. Now maybe it's time to give some results. So I'll start here. In the 70s, people started in interest in the behavior of extreme values of the branching random walk. So if I look at the minimum value of branching random walk, the minimum value in a given generation. So let's say I look at the third generation. So I have 2 to the 3 values. So I have 8 values, and I look at the minimum value. So in my picture, it's this value, the value represented by this cross. So what I'm interested in is when the behavior when n goes to infinity. Okay, you are going to tell me that if you take whatever given branch, then the value of v of x, by definition, is just the sum of n independent random variables, each having the same distribution as xi. So the law of large numbers tells you that v of x is more or less n times expectation of xi. And we know that expectation of xi is strictly positive. Yes? But since I'm taking the minimum over 2 to the n, so an exponential number of random variables, so you would expect that something unusual happens here, and it does. It turns out that almost surely it converges to 0. There is nothing special about the value 0. I mean, without this assumption begins to prove that this is true, except that the value, the numerical value could be different. So under these 2 conditions, that the numerical value is simply 0, and that's it. Okay, so it goes to infinity somehow sublinearly. There is something, a phenomenon of large deviations happening here. So along each branch, somehow you have a positive drift, but if you have an exponential number of branches, and it's somehow that there are particular branches along which the value of a branching random walk is particularly small. It costs you an exponentially, but I mean, you are very happy that you get a value which is smaller than the normal value, which is n times expectation of xi. So that's, well, it's not really an explanation, but that's exactly what happens. Okay, anyway. Biggins also looked at the minimum value without normalization. And he proved that without normalization, it goes to infinite almost surely. Well, this part is not very surprising in the sense that we know that for a given branch, along a given branching, it goes to infinite even linearly. That's law of large numbers. So if you take the minimum, somehow it's not a big surprise that it still goes to plus infinite uniformly along all branches. Okay, so we know that if you admit these 2 lines, so we know that this guy goes to infinite, but sublinearly. So a natural question is at which rate? So McDiarmid asked already this question in the mid-90s, sorry. So usually when you have something which, so actually this is a law of large numbers. So the next question you are asking is there any kind of central limit theorem? So usually in the second order you have square root and the limit is standard Gaussian law, which is not going to happen here. So McDiarmid tells you that this is false. He proved that the second order is at most log. So he proved that there exists a constant depending on the law of Xi, such that this guy is at most a constant times log, so which is very, very small. So it cannot be as large as square root of n. So we know something which goes to infinity, but at most at the rate of log. So it goes to infinity, but very slowly. Yes? So here is my first theorem. Yeah, something very special happens in this setting. So my first theorem says that the result of McDiarmid is optimal. I mean, you cannot improve the log rate function. So it turns out that in probability, it converges to a very nice constant, which is 3/2. So I hope at this time, at least even if you don't know why, you are fully convinced that these two conditions are really the good conditions which ensure you a universality result. Because as long as you assume this, then you have something which at a limit you to something which has nothing to do with the law of the branching random walk anymore. I mean, it's something universal. Just as for the usual random walk, if you assume these two, then you know that the limit is just standard Gaussian law, and it has nothing to do with Xi anymore. Okay? So I hope it's very convincing, even if for the moment it's not clear why you do need this and that. And we still need 5 more minutes to see that they are very natural conditions, actually. For the moment, let me continue with the presentation of first theorems. So you have something which converges in probability. A natural question is, can you strengthen the convergence? Do you have almost sure convergence? And the answer is no. If you look at upper and the lower limits, there are some fluctuations. The upper limit is like in convergence in probability is still 3/2, so that's almost surely. But the lower limit is slightly smaller, it's 1/2. So somehow, typically it goes like 3/2 times log n, but somehow along some special subsequence, it can be as small as 1/2 of log n. Okay, so maybe some comments about this first theorem. So the first part, convergence in probability, actually this is something which is proved also by Adair-Behe and Treat in 2009, I think. So they also prove this one, and not only they were able to prove this one, but they were able to prove a lot more. In particular, they also were able to prove that not only you have convergence in probability, but even the mean of, you take the expectation of this one, is still converged to 3/2, and they were also able to give some estimate about the deviation probability. So the probability that this, the difference between this guy and its expectation is beyond a given given number, they are able to prove that it's at most exponential. So they are able to prove a lot more than what I wrote it here. So that's what Adair-Behe and Reed did. And you can even do more. That's what's did by Elie Aydekun. It was posted on arXiv, so it's going to be published either this year or next year in the Annals of Probability. And he said that you don't even need to divide by log n. Somehow, if you look at the minimum and you remove the 3/2 log n, and you still have convergence in law this time, you need to assume something more. You need to assume that there is a non-lattice condition, because otherwise it's possible that things stay bounded, but they don't converge. So somehow it turns around cyclically. So you need to assume an additional non-lattice condition. Then Aydekun is able to prove that the difference between minimum and 3/2 of log converges in distribution to a non-degenerate limit. So this is a very strong result. For the lattice case, Professor Lifshitz is able to say a lot more in the lattice case. So these comments are to say that actually you know a lot more than the first line. Okay, and in the case of branching Brownian motion, all these things are known to Bramson. So in the paper by Bramson in '78, Bramson was able to prove that, and he was able to prove what Idegon proved. Well, almost 30 years later, but the proof of Bramson was very, very technical. I mean, it required more than 100 pages, and the proof of Idegon required more than 60 pages. So, I mean, these are very highly technical proofs. Okay, so I wish to present you another result. So this time I changed a little bit my mind. So instead of the minimum value, actually I suggest that we sum over all the 2 to the n values of branching random walk in the nth generation, but I don't take the sum of the positions. I don't sum of the exponential to minus of their positions. Okay. The reason for which I'm looking at this guy is that under this part of the assumption, I immediately see that it's a martingale. So that's the reason for which I like this quantity. Somehow I immediately see that this is a martingale. And this martingale has a name in the literature. It's called additive martingale. Why it's additive? It's very simple. I mean, there is no deep meaning as far as I know. It's because I'm summing over something. So that's called additive martingale. That's it, okay? This martingale, of course, is positive. So everybody knows that additive martingales just converges automatically. You don't need any additional results. So that's one of the fundamental results in martingale theory. So you already know that with probability 1, which we called almost surely, it converges to something. The limits I will call W infinity. Even though everybody is positive, nothing guarantees you that the limit is still positive. It could be 0. Okay? So for the moment, all I can say is that it's non-negative. So it's the same paper as the one which I cited a few lines before. Begins in '78, prove that actually under our assumption. So for the moment, I only need the first part of the assumption. I already know that W infinity exists. Begin say that if you assume moreover the second part, then actually this guy is 0. So I have a positive martingale, but somehow, very unfortunately, the limit is 0. So it means that it's not uniformly integrable. And the question was, if you have something which goes to 0 with the probability 1, so the natural question is what's the rate at which it goes to 0? In the literature, the question is called the Senator height norming problem. And before I give you the answer to this question, let me present a motivation of all this, because I started my talk without giving you any particular motivation. Why do you want to study this and that and so on? So maybe it's time for me to tell you a few stories about branching random walk, and it's continuous time analog. So okay, I start the motivation part in the middle of my talk. Actually, okay, the study of branching random walks goes back at least to the 60s. So a lot of Japanese mathematicians made some fundamental contribution to the study. But somehow the study became much popular in the 70s thanks to a paper by Henry McKean. And McKean was able to make an explicit and very simple connection between, on the one hand, branching Brownian motion, so it's a continuous time branching random walk, and the so-called traveling wave solution of the FKPP equations. FKPPF is very simple, it's Fisher, and KPP, I always have some trouble to pronounce the name. They are three Russian mathematicians. K is Kolmogorov, so Kolmogorov. P is Petrovsky, and the second P is Piskunov in French, so Piskunov. Okay, I'm not going to write their names because each time I try to write down their names, I make a mistake somewhere, at least one mistake. It's a very nice class of partial differential equations, and what was interesting in McKean's work is that McKean was able to give explicitly traveling wave solution to these FKPP equations using branching Brownian motion. Okay, I will write down the solution of McKean just. So here is the solution of McKean. Double dot means definition. I'm not going to use it anymore, just to give you some flavor of his solution. So he used the expectation of exponential to minus c, just as capital C is a constant which is not important at all, e to the minus x, and the w infinity, which is a random variable, a real valued random, well, it's a non-negative random variable. So that's what McKean used, and he said, look, I have a proof to say that this is a traveling wave solution of FKPP solution, FKPP equation. I wrote deliberately W infinity to indicate that it's exactly the same random variable which we wrote it here. But now you see the problem that according to Biggins, W infinity is 0, which McKean didn't know in 75. At that time, he used the limit of a positive martingale, so he thought that it must be strictly positive, which is not true. So a few months later, McKean published an error time saying that, okay, there was a problem with my proof because I assumed that this is positive, but nothing guarantees that it's positive. So at that time, it's not clear what's the truth. And a few years later, we know that there was a problem with McKean's proof. Well, it doesn't matter because only a few years later, Lally and Selke, 87. So they said, okay, McKean's work is all right if instead of taking this one as a traveling wave solution to FKPP, I'll take another one. So they use another random variable, which is non-negative. Actually, they prove that this one is positive. So now I need to tell you what D infinity is. So everything is done for branching Brownian motion. So for discrete time, so this was proved by Biggins and Cipriano in 2004. So they look at something which is very similar to the additive martingale, but except that here, instead of taking exponential to minus the position V, I also multiply by the physical value of V. It's not very hard, actually. It's a very simple exercise to check that under my assumption star is still a martingale. So this guy is still a martingale. I need both identities to check that it is a martingale. So this one is called derivative martingale. Why is it derivative? Because it's the general term is the formal derivative of, well, if you remove the sign minus, the formal derivative of the e to the minus v of x if you make a derivative with respect to v. Yes? You have a martingale, but, well, when I was here, the convergence is automatic because I have something which was positive. Now the derivative martingale could be positive or negative. So in principle, there is nothing which guarantees that it converges. So Biggins and Cipriano, or rather Lally and Selke for branching and Brownian motion, they prove that you still have almost sure convergence. So the limit, I call it d infinite. And what's really important is that the limit is still strictly positive. So that's a bit difference between the new martingale, which I call the derivative martingale, and the previous one, which is which I called additive martingale. So if you use the new limit, then it turns out that everything works. Okay. Just some comment to say that it's not that mysterious. Okay, I'm cheating. Actually, to prove that this is true very rigorously, you need to do a lot of work. But intuitively, it's very hard to convince you that it should be true, because I remind you that according to Biggins, so the second line, according to Biggins in 78, I know that the minimum goes to infinity. It means that if with probability 1, for all n sufficiently large, v of x is very, very big. So a fortiori, it's positive. Yes? So for all n sufficiently large, unfortunately, whole large depends on omega. So for all n sufficiently large, everything is positive. So if this is positive, then you have a martingale which is positive. So of course, it converges. And so what's really important is to say that the limit is strictly positive. Yes, of course, that's not a rigorous proof because whole large n should be really depend on omega. So it's not a rigorous proof, but at least I hope nobody gets surprised that it still converges. So what's really important in this result is that the limit really is strictly positive. Okay, so now let me state my second result, and that's the end of the statement. I knew that my additive martingale converged to 0 with probability 1. So the question was at which rate? It turns out that it goes to 0 polynomially. If I multiply by square root of n, then in probability, it converges to a positive limit, which I should not forget. A very nice constant, square root of 2 over pi sigma square times the positive random variable, which is d infinite, when n goes to infinite. So now I need to tell you what sigma square is. Sigma square, by definition, is the expectation of sum over the two vertices in the first generation of vx square e to the minus v of x. Again, you are going to tell me that I don't like your writing, then you see that this is exactly twice expectation of xi square e to the minus xi. Okay, if you prefer. Now maybe I should say one more word about the mysterious integrability condition, which I didn't want to tell you. Okay, it's there to ensure that this guy, and that guy they all have mathematical meaning. I mean, they are well defined. Actually, I need still slightly more than that, but I mean, from practical point of view, it's just to ensure that all the three expectations have mathematical meaning. Okay, again, as before, if you have convergence in probability, you could ask yourself, is it possible to make it into almost sure convergence? And the answer is no. We also know that. Along a exceptional subsequence, we are able to prove that this guy goes to infinite. Okay, so these are all I want to tell you. So now maybe time for the proof. I still need a quarter, so that will be the second and last part of my talk. So I prefer to prove just the first theorem. And before I start my proof, I should give you the unique tool I know of. This is the only tool I know in the study of branching random walk, and it's written down explicitly. I copied it from Biggins and Cipriano, but actually it was known a lot earlier by a whole bunch of people, more or less starting from the mid-70s. Every 4 or 5 years, some clever guy found this by himself in his own language. So in the literature, every 4 or 5 years, you found a paper which written in a totally different language. That's why nobody realized that, I mean, they were using exactly the same ideas because the language used were completely different. So I could find the name of Biggins and Donny in 75 and Kahn and Perrier in 76. These are the very first names I could find, but it's not totally impossible that some clever guy knew that also even before that date. So they claim the following things. So I take whatever n. So I fix a level, which is the generation. So let's say n. I sum over all the 2 to the n vertices in a given generation. Here is the nth generation. And I take whatever function of the branching random walk. And no, I need, so for any function defined on Rn, okay, we are studying probability, so I need to make sure that everything is measurable. Otherwise, will have trouble to define my expectation. Now I need to tell you what I mean by v of x1, v of x2, and so on, v of xn. So I need to use my, oops, sorry. Here is my nth generation. So in my picture, n is 3, yes? I took the sum over all the vertices in the nth generation, all the vertices x. So let's say I take this vertex. This is my vertex x, yes? This guy has a unique father or mother, if you prefer. This is this one, yes? This one has a unique father, which is the grandfather or grandmother of x, yes? And at the very beginning, everybody starts from this guy, yes? So my notation is that this is the ancestor of x in the original, which I called x0. I don't even need to x0. And this will be called x1, which is the grandfather of x in the first generation. Yes, and this and so on. This is x2 until x is xn, because I'm taking x in the nth generation. I hope the definition of xi is perfectly clear. Yes, so I'm looking at not only a function of the branching random walk, but I even keep track of all the history, all the genealogy. So I look at v of x1, v of x2, until v of xn, which is v of x. So I take whatever given measurable function of all the history of branching random walk, and I sum over all the vertices in the nth generation. Okay, so that's the meaning of what I'm looking here on the right-hand side. Sorry for the noise. And Biggins and Cipriano tells me that it's something very simple. On the left-hand side, it looks very complicated because I'm making a sum over 2 to the n branches. Along each branch, I know it's very simple. It's just a random walk with with drift, which is Xi. Everybody has expectation Xi, right? Biggins and Cipriano tells me that actually things become very simple. It's exactly the expectation of the same measurable function g. Okay, you might worry about integrability. So let's say to be non-negative, then everything is perfect. Biggins and Cipriano say that, okay, it's the same expectation of the same measurable function of another random walk, which I call S. So S is a random walk, which means that Si minus 1 for positive I, they are IID. Okay, I assume that S0 is 0. So you see that on the left-hand side, you have a whole bunch of random walks. That makes the study very hard because the number of branches is exponential. On the left-hand side, things are very simple. You just have a usual random walk. But this is not exactly true. If I want to make it to be true, I need to add a density. But the density is very simple. It's exponential to the terminal value. Okay, if I want this identity to be rigorous, I need to tell you what the new random walk Si is. So I need to tell you what's the law of S1. So S1 is such that the expectation of whatever measurable function from R to R measurable. Oops. Okay. Again, I assume it's non-negative to avoid having integrability conditions. And this is just expectation over the sum over the two vertices in the first generation, exponential of v of x, h of v of x. Oops. Well, this is just it's the definition of this identity when n is to 1. I mean, these two are absolutely identical if you take n to be 1 on the left-hand side. Okay. You said, why is this true? I don't see why this is true, and I say that this is trivial. I'm not going to give you a proof of this because it's really trivial. I mean, you can give it as an exercise to all your undergraduate students as long as they know, for example, what conditional expectation is. Why is it true? I can prove it just in words, yes, by induction n. For n equal to 1, it's just a definition of the law of S1, nothing to prove. Assuming that this is true for n, then I say that it's trivial to prove it for n plus 1. I mean, all you need to do is to check what happens in the first two generations. So maybe I can use the picture here. Assuming that this is the n plus 1 generation, all I need to check is what happens in the first two vertices, and I look at the subtree of this guy and the subtree of that guy, and I use the induction hypothesis for both subtrees, and I make a sum, and I immediately get that. So the proof is just one line and nothing very special. Okay, so the proof of this guy is trivial. What I don't explain, and that's for some very deep reason, is why you should have this peculiar new random walk. Because I make a trivial observation, is that under my assumption, I realize that the new random walk is mean 0. That's something very new, because on the left-hand side, I told you that along each branch, everybody has the distribution of Xi and expectation of psi is strictly positive. But I have an exponential number of branches on the left-hand side. On the right-hand side, I only have just one single random walk, but this one single random walk is very peculiar, and it's something totally new. It has nothing to do with all the previous random walk, but this new one has expectation 0. So this is something really new, and there is a very deep reason for the presence of this new random walk on the right-hand side. Unfortunately, I don't have enough time to explain you why this is true, but let me give you an indication of why this should be useful. So I have less than 5 minutes to give you a proof of first theorem, which I will write it here. So I fix epsilon. I just prove one part of the theorem. So it's not going to give me the full statement of the first line of the theorem 1, but at least it will explain you why you should expect to see log here. Why should this mysterious constant 3/2 pop up? I think that's the most interesting part. Okay, so I fix a very big constant, let's say capital K. I fix a real number which I call small of a. And I count, which I write it as Zn. I count the number of vertices in the nth generation such that at this vertex, the branching random walk is smaller than small a of log n. And moreover, from the beginning until this vertex, everybody is greater than minus k. So I count the number of vertices in the nth generation such that this is true. And I'm looking at the probability that this is strictly positive. Since it's a counting number, saying that this is strictly positive is equivalent to say that it's at least 1. So I can use Markov inequality, which say that this is smaller than the expectation. Of course, I prefer expectation because then I can use this Bigins-Kipiano formula saying that, okay, I know that the value of the expectation, and on the right hand, it's expectation of e to the Sn, the indicator function such that the terminal value should be smaller than a of log n, and such that between 1 and n, everybody should be greater than minus fk. Yes? And I say that, okay, this is trivial because on this event, exponential fn is smaller than or equal to n to the a. Yes? So maybe I should write it here. This will be my last line. So this is smaller than n to the minus a. Expectation of the indicator function is just a probability. So that's the probability such for a random walk, the terminal value should be smaller than a times log n, but such that everybody is always greater than minus a constant for all I between 1 and n. And I remind you that Si is a mean zero random walk. It's a simple exercise. Actually, I learned it from Yuval Paris. He explained me in 5 minutes that it's trivial to see that this guy is n to minus 3/2 plus a small of 1. You can replace n to the 3 small of 1 by log n squared in my case. He has a very simple argument to say that. So you see that as long as a is strictly smaller than 3/2, then this goes to 0. If a is strictly smaller than 3/2. What I claim that if a is strictly smaller than 3/2, then in probability, this goes to 0. And then I say that I can remove this guy because I remind you that, okay, I forgot. My martingale, my additive martingale automatically converges. So, whoops. I take whatever minimum value, it's always bounded from below. Actually, I even knew that it goes to infinite, but I don't need to use this strong result. Or I need to say that it's bounded from below. So for any given epsilon, I can always choose capital K sufficiently large such that everybody is greater than capital K. This happens with probability at least 1 minus epsilon. So this is a free condition. So this is sufficient to prove this line. And that's the end of my proof. Thank you very much.
Questions? You probably should mention that more general branching mechanism.
Sure, yeah. Yes, of course. Yes, I started with a so-called an example, and I told you that probably I wouldn't be able to go beyond the example. So this is a simple example of branching random walk, but actually everything, so in the simple example of branching random walk, I assume that everything is IID copies of a given random variable, but I really don't need to assume that among the brothers, whoops, I really don't need that these two are independent, and I don't need them to be identically distributed either. So that's why you see in my assumptions, I never use any other writings. If you write the sum, then you see that you don't need neither independence nor identical distribution assumption. So everything is still true without this IID assumption. But okay, assuming that it's IID, of course, it makes the presentation of the model a lot easier. But technically speaking, you see that if you check this, you don't need IID assumption. So it doesn't make your life easier if you assume it's IID.
What is the FKPP equation?
Oh, okay. The FKPP equation, I think it's partial differential equation. It's called du dt. It's 1/2. If I stop here, it's just the usual heat equation. Then it's plus U2 minus U. Actually, you can put it a lot more general. It's just the moment generating function of branching mechanism. In my case, it's just a binary. That's why I have U2. Otherwise, you can have whatever series. It's still all right. So it's a nonlinear partial differential equation. And it turns out that for this equation, it has a so-called traveling wave solution. It means that, okay, I'll write it this way. If you start with the initial value, this is W, whoops, I use it. Oops. If this is the initial value of U, so this is U0 dot, yes, then it turns out that when T goes into infinity, somehow you have a force push it to the right, and it keeps going down like this. With the speed is square root of n, square root of 2. For large T, it becomes very smooth, and it moves with a constant speed. It means that the distance between this guy and that guy is roughly speaking square root 2 times T, and otherwise, asymptotically, it's the same thing, so it just moves to the right. And it turns out that it's very easy to construct the traveling wave solution to this equation using branching and Brownian motion. Well, so that's the main reason for which Brownian motion becomes very popular in the 70s.
And where in these equations is W of x?
Oh, okay. Yeah. Excuse me. Okay, so I should not. If my writing order maybe is the converse order of what McKean was writing. I think McKean was writing it in different story. If I take a solution of okay. Maybe. Okay, I think I prefer to use this one. I told you that there is a traveling wave story. So if I make some make a linear transformation here, then as t go to infinity, it converges to this red story things, which called W of x. And I told you that this guy is square root of 2 times t. You have a linear speed, and W has also a plus. I should not confuse. So this square root of 2 is the speed of the traveling wave. Otherwise, you find all the rest of the FKPP story, and there is a one-to-one correspondence between FKPP and this traveling wave story. That's the converse of this is always true. If you define, so that's the definition of U function of 2-parameter function U as W of x minus square root of 2 times t, then you will recover FKPP story. So you can pass from one side to the other. I mean, the transform is 1-to-1. Of course, I didn't give you the exact form of the traveling wave solution. Since I'm writing it here, maybe I should write one more line so that nothing remains mysterious. So this here is McKean's construction of traveling wave solution of FKPP. He just take the minimum. Okay, this is not the same t, the same x. Let's say U of t. You take the minimum of the Brownian motion. So you need to be more careful. In my case, time is decreased, whereas you really should use continuous time setting. And you need to use so-called Brownian motion instead of usual random walk. So this is the minimum value of Brownian motion at time t. You look at the probability that at time t, everybody is beyond the position minus x. Then the proof is just 2 or 3 lines using strong Markov property and nothing more. And that's it. So once you are told the story, then it's trivial to check that. If you define this, then it's trivial to check that U is a solution of FKPP. Well, things becomes a lot easier when you are told the truth. Of course, what was difficult was to find it by yourself. Thank you.